This is 12.2.3, Electromagnetic Waves. Now we're going to start with Maxwell's theory. And Maxwell said that light were made of two oscillating fields, which is an electric field and a magnetic field. And that the oscillating electric field caused a changing magnetic field, and the changing magnetic field caused a changing electric field, and the changing electric field caused a changing magnetic field, and so on. And that's how electromagnetic waves propagated. Now Maxwell, he did all of his work theoretically by solving equations. You won't need to solve any of his equations, but you will need to appreciate what his value for the speed of light was and the components that made that up. So his theory said that you've got two fields, which is a B field and an E field, and these fields are perpendicular to each other. So in terms of looking at it three-dimensionally, if we have a wave which is propagating along this line, and what I will do is in different colors I'll draw the different fields oscillating. So if that's our B field, then our E field in a different color will be oscillating perpendicular to that. Yep. They are, yes. Yeah, they're in the X and the Y. So imagine in 3 dimensions, you've got an X and a Y and a Z. So if it's propagating in the Z axis, then the B field oscillates in the Y axis, the E field oscillates in the X axis. And you can rotate this any way you like. Yeah, and that's what polarization is. The polarization is all about what orientation is its E field in. Whatever orientation the E field is in, if I rotate this around any direction I want, the B field will always be 90 degrees to the E field. And the direction of propagation will always be 90 degrees to that because it's a transverse wave. So EM waves are transverse with a electric field vector oscillating perpendicular to a magnetic field vector. Now the evidence for this is to just make an electromagnetic wave. So if we have an oscillating electric field inside a wire, that produces an oscillating B field. And the oscillating B field produces an oscillating E field. Now, through his work, Maxwell calculated the speed of light, and he got the speed of light to basically be 3 times 10 to the power of 8 meters per second. And then experimentally, other people also got the same value, which confirmed that his maths was correct. So we'll just write down the evidence. So oscillating E field in a wire or spark gap generates an oscillating B field, which generates, or we can say induces, an oscillating E field. And that carries on. And Maxwell's formula for the speed of light is given by C equals to 1 over the square root of mu naught epsilon naught. Now, epsilon naught, you guys already know, is the permittivity of free space. It's how difficult it is for an electric field to exist within that space or within that medium or lack of a medium. And mu naught is the permeability of free space, which is the same analog but for a magnetic field instead. So it's how easily a magnetic field permeates a space. So epsilon naught, the permittivity of free space, which is equal to 8.85 times 10 to the minus 12 farads per meter. And it is how difficult it is for E field to exist in that space. And mu naught is the permeability of free space. And it's equal to 4 pi times 10 to the minus 7 henries per meter. It's a unit. Now, you don't need to know this number off the top of your head because it's given in the formula booklet, but you need to appreciate that just how epsilon naught relates to how an electric field will exist in a space, mu naught is how a magnetic field will exist in that space. Let's start a new page. And we'll now look at Hertz's discovery of radio waves. So, Hertz discovered radio waves by using high voltage currents in a coil with a spark gap, generating a spark, and then from that spark gap, he saw that he was then able to detect it by using a wire loop that was at a distance from that spark gap. So, if we draw a coil and it's connected to high voltage AC, the high voltage AC causes a spark between this gap. That's a spark. And from that spark, he was then able to detect them with another coil further down. So this is the detector coil. And the reason why he was able to detect it is because those oscillating E fields and B fields would induce an oscillating potential difference, or EMF, in the detector coil, causing that to spark, or to generate a potential difference. So the waves were coming out, and they spread out as they move further along. So the spark caused emission of radio waves. Radio waves are electromagnetic waves. Which means that they have E fields and B fields. The changing B fields, induce EMF in detector coil. And a spark is seen. Now he experimented with these, so he used different materials to see if these electromagnetic waves, or the radio waves, would interact with different materials. So when he used insulating materials allowed partial reflections of the radio waves, acted kind of like a mirror that partially reflects the radio waves. When he used conducting materials like sheets of metal, he found that they could serve to block the radio waves because they were reflecting radio waves. He found that if he curved the sheets of metal, they acted like reflecting curved mirrors, almost like lenses, which served to focus the radio waves. And if he focused the radio waves at a particular point, then he could measure them a lot easier because they would increase in intensity rather than spreading out. So, he used these experiments to find the wavelength of the radio waves. So, 1. Block radio waves. And he did this by using a sheet of metal to block the waves reaching the detector. And number 2, he found the wavelength by creating stationary waves. So, the way that he would do this is if he had his spark generator here with his AC. These sparks would generate a wave. On the other end, he would have a sheet of metal which would serve to be a reflector. That would then create stationary waves. And on the other end of that, he would use a curved reflector so this is a curved reflector to focus waves. Now he would put his detector in between and he would move it around. As he moved it, he would find the areas where nodes and antinodes existed, and he would move his detector across several nodes, and then using those he would find the wavelength of his radio waves. So the distance between two nodes is equal to lambda over 2, half a wavelength. The distance between 3 nodes is 1 wavelength. The distance between 4 nodes is 3 over 2 wavelengths, etc. Yeah? So you take 1 away from the node, and then you half it, and that would give you how many wavelengths that distance is worth. So move detector over several nodes, and then calculate wavelength. And he found that the wavelength for the radio waves was about 66 centimeters. Then, third thing that Hertz did is he demonstrated that his radio waves were transverse waves. So demonstrate that radio waves are transverse. And this was quite simple, is that the radio waves, he found they were polarized. And he found that by generating the radio waves and then rotating his coil around by 90 degrees and finding that the intensity of the waves received by the detector decreased and became 0 at 90 degrees. So if we just draw the spark, and our detector coil, and we'll say that rotating the detector by 90 degrees decreased the intensity of the received radio waves until it reached 0. So this shows that the radio waves were polarized. And if they're polarized, if radio waves are polarized, then they must be transverse, because polarization is only a property of transverse waves. So they must be transverse. Now, the radio waves were generated by an alternating current, and he knew the frequency of his alternating current. Therefore, he knew the frequency of the waves being generated. So we'll do speed of radio waves. F was known because it's the same as the AC used to generate the radio waves. Lambda was found through experiment. So now he could just use the wave equation, C equals to F lambda, to obtain the speed of his radio waves. And the value that he obtained was extremely close to the value that was given by Maxwell's calculations. So his value of C was very close to Maxwell's value. And so if they both obtained basically the same speed, Maxwell's was done for electromagnetic waves, which you didn't really know what these were. It was a theoretical thing. And Hertz got the same value for these new waves that he discovered by making sparks. That meant that the radio waves must be electromagnetic waves. So whatever Maxwell calculated theoretically and whatever Hertz discovered experimentally must have been the same thing. And we'll move on to the last bit for 12.2.3, which is Fizeau's experiment. Now, Fizeau's experiment was about finding the speed of light, and he used this by using quite basic tools over long distances. So he had a light source, which is the sun. Yes, start a new page, please. So this is the light source. For example, the sun. Then he had a partially reflecting mirror. also known as a semi-silvered mirror. So partially reflecting mirrors will reflect half of the light and will allow half of the light to transmit. Then, at very far distances, he had a plane mirror. And he also had a toothed wheel. So what would happen is light rays would come down from the light source. They would reflect from that partially reflecting mirror. They would go past the toothed wheel, and from the toothed wheel to this plane mirror would be a very long distance, which could be several kilometers. Once that ray of light struck that mirror, it would reflect. It would come past the toothed wheel again, go through the partially reflecting mirror, where it would then be detected by an observer. And you could have this, for example, the rays flowing into, say, a darkened environment. So a simple case would be, you can imagine like a tunnel. If you had a ray of light going into a tunnel, so it's easy to detect this light. Now what he did was, when stationary, you can imagine light will just reflect and go to the observer. When the toothed wheel begins to rotate, instead of seeing light, you see pulsating light. So you see flashes of light, because the teeth sometimes block the light. And if you keep increasing the frequency of the rotations of this wheel, then at one point what happens is, when light passes through a gap and reflects, when it comes back, it's then blocked by a tooth. And if that is what's happening at a certain frequency, that means that no light is then seen on the other side at that frequency. So if you know the frequency that it takes for the rotation, we can then make a formula that will tell us the time that it took for light to travel that distance and come back and be blocked by that toothed wheel, because no light was seen. So let's make some notes on this. So when wheel is stationary, continuous light is seen. Continuous light is seen. When wheel is rotating, pulsating light is seen. And at a particular frequency, no light is seen. So the explanation for that is, as I said, light which passes a gap is blocked by the next or the adjacent tooth. The distance has to be large, yeah. If the distance is not large, then the frequency that you need to rotate this is going to have to be extremely big. Yeah? So the larger the distance, the slower that frequency will be, which means that it's realistic. Now, if there are n number of teeth and there are n number of gaps, then the total teeth plus gaps is equal to 2n. So if there are n gaps and n teeth, total teeth plus gaps equals to 2n. The time it takes to rotate by one tooth or one gap is going to be the period, capital T, divided by 2n. So time to rotate by one tooth or gap T equals to the period over 2n. So here we can say T is period. Therefore, frequency is 1 over T. So if we sub that in now for the frequency, the time taken is 1 over 2nf. And that time is the same time it takes for light to travel that distance, reflect, travel that distance again, and reach that tooth. So light travels to the mirror or to the plane mirror and back in that time. Therefore, distance equals to 2d. So then we know that the speed of light is equal to the distance it traveled divided by the time it took to travel that. So c equals to 2d over little t. So this is from v equals to s over t. And then we have to sub both of these in. So if we got t equals to 2nf, then 1 over t is equal to 2nf instead of 1 over 2nf. So sub in 1 over t equals to 2nf, and we get c equals to 4dnf. Now, when Fizeau did this experiment, he obtained a value that was only slightly higher than Maxwell's value for the speed of light. So Maxwell's value theoretically was like 2.99 something something times 10 to the power of 8 meters per second. And Fizeau got a value of speed of light just over 3 times 10 to the power of 8 meters per second. So we'll write that here as well. So Fizeau obtained a value for C just slightly greater than Maxwell's value. So essentially, Fizeau basically got the same value as Maxwell. And so that meant that light was also an electromagnetic wave. And the speed of light was now determined. So what Hertz discovered as radio waves, which are electromagnetic waves, had the same speed as light, which was the same as the speed that was determined by Maxwell mathematically. And so all of these things are part of the electromagnetic spectrum. And that's the end of 12.2.3.